Everyone. So it's my great pleasure to introduce Professor Gershon Wolansky. He is a professor emeritus at the Department of Mathematics at Technion, Israel Institute of Technology in Haifa. He obtained his PhD in mathematics from Courant Institute of Mathematical Sciences at New York University in the year 1985. So his research lies at the interface of linear and nonlinear partial differential equations with important contributions to optics, vision, optimal transport, and fluid dynamics. And he is a co-inventor in collaboration with Jacob Rupinstein on several patents in optical design and related technologies. For example, vision correction, free-form optics, illumination control, and ray mapping. Okay, so without any further delay, let me extend a warm welcome to Professor Wolansky. And this week, he will be speaking on from optimal transport to optimal networks, discrete and semi-discrete optimal transport.
Thank you very much for the kind introduction. I'm very happy to be here. And I guess that my talk is a little bit outside the scope of the conference, so I'm not going to assume a lot of prior knowledge on the optimal transport. So this is more or less kind of a graduate level course. But maybe if time permits, I will introduce some special aspects which are interesting for me and maybe some open problems if time permits. So let's do first some history. Where did it start from? So in the 18th century, Gaspar Monge published a paper. My French is not so good, but Mémoire sur la théorie de Debabrata et de Rambali. So what is this? The idea is that we have a pile of dirt, and we want to move it to another excavation, something like this. We want to send stuff from here to here. So this is a one shape, call it mu1. If you can think about it as a distribution of some material, just mu. And this is another distribution mu, and we assume that they have the same total mass. And it costs some price to move 1 unit of mass from point X to point Y. So this is C, X, Y. This is price to move from X to Y. And in Monge's case, it was just the Euclidean distance. Monge considered just the Euclidean distance between X and Y. And he asked, what is the mapping T, which push mu to nu, and later I will explain precisely what it means, such that which minimize the cost. So the cost is the integral of C x, the cost from x to tx over the integral over the mu, over the distribution here. Of course, Monge himself didn't think about, didn't know what is it measure, but this is a modern terminology. So this is the cost, and we want to minimize it over all the mapping that satisfy this constraint, that push mu to nu. Of course, Monge, it was a very prominent geometer, but he was also very interested in optics. And let me say a few words about optics, even though this will not be part of the course. So Monge had two students Dufin and Veloz, I think, and they were considering a problem of distribution of light rays. So, and they observed that there is a really that the path of transport from point X to point Y here is along, they are determined by paths which are perpendicular to some surfaces, and this is surfaces are later known as to be the phase surfaces of a light beam. Anyway, so this was back in, excuse me. This was back in 1781, and then okay. And then after some time passed, and in 1942, Leonid Kantorovich published a paper on the translocation of masses. And between these two papers, almost nothing was done. So except for some, like I said, some observation about the form of the phase surfaces connecting with the Monge problem. Almost nothing was done. What Leonid Kantorovich then invented what is known today linear programming, and he found that the Monge problem can be relaxed to a kind of linear programming which has a solution. Anyway, then another time passed, and in 1987, there was a short paper of Jan Brenier, and this was the beginning of explosion. The paper followed composition of monotone rearrangement of vector fields, which was really a breakthrough, and from this time on, this is just exponential growth of material. I think there are tens of thousands of papers published related to this field. But it's not precisely true, because between Kantorovich and Brenier, which we call the quiet period, there was some prominent contribution. Studakov in 76, he made a contribution to Monge problem corresponding to norm. And by the way, Aldo, one of the speakers today, has also a very prominent contribution in this problem. And then Norton Smith in 84, they predated Brenier and proved some characterization of optimal maps, which used by Brenier to prove his unique solution for law decomposition. Anyway, there are many things in optimal transport which I will not cover, including regularity, including Monge-Ampere equation, which is very relevant here, including Ricci curvatures and CD spaces, curvature dimension spaces. All these very important subjects I will not cover because I want to make it more elementary, and not enough time for this. But what I sketch here is some overview of my plan for this week. So I will start by some non-orthodox way in discussing discrete matching. This is called also the marriage problem, which is a discrete analog of the Monge problem. Then I will move to semi-discrete, which when the target is a finite space, but the source may be infinite. Then I will we will discuss the in detail Monge and Kantorovich, prove the duality formulation, C-concavity, then I will discuss one-dimensional problem and some nice application, which I like very much for the circle mappings. Then I will use this to discuss the metric Monge. Again, this is the problem with metric distance, and the Beckmann problem, which is related. Flow and dynamical formulation is also a subject that we will discuss, I hope. And finally, limit theorem and branching. Okay, so okay, so this is more or less the program. I hope to finish it all because especially in the last part, there are some open problems which can be very interesting to some of you who may want to pursue this. Anyway, let us start with the discrete case. So, Gede Shapley, in 1962, they published a paper which is called College Admission and Stability of Marriage. What does this have to do with our subject? So, what is the marriage problem? Suppose we have a group of n men and n women. This is man, the woman. And each man grade the woman according to a preference list, and each woman grade the man according to her preference list. So each one of the men and women have a preference for all the other. So so eventually each man and each woman find match together and form and they're married, and they get and we can become married couple. So the marriage assignment will be called stable if there are no so-called blocking pair. What is a blocking pair? So suppose we have this matching, man 1 to woman 1, man 2 to woman 2, and so on. So if, say, man 1 prefer woman, say, 3 over his wife, and woman 3 prefer man 1 over her husband, then this is unstable. The marriage will break. And the question is there always a possibility to arrange, to match them in a stable way? And it's not so obvious because you see the analogous question, if there are only one gender, or for example, consider a group of tourists who come to hotel, and they have to be accommodated in pairs in hotel rooms. And again, each tourist have a preference list for the other. In this case, there may be no stable matching. There are cases where no stable matching exists. In this case, there is always a stable matching because this is a bipartite structure. We have two groups, and what Gell and Shapley published is a very simple and intuitive algorithm how to find such a stable marriage. And so the algorithm is like this. Well, suppose each man, at the first stage, each man proposed to the women on the top of his list. So at the end of this stage, some women may get proposal, maybe more than one. Maybe a woman we didn't get anything, but each woman who got more than one proposal, she accepts the one which is the best in her list from those who proposed to her, and release the other. So at the end of stage one, there are men which are engaged, and all the other those who were rejected. They now propose to the second woman on their list. And again, the process repeats. The woman who gets another proposal, which is better than the one she had before, she releases her fiancé and accepts the new one if he is higher on her list. So after a finite number of iterations, the process finished in a stable matching, and this is very easy to see. So it's very surprising that for such a simple, apparently simple idea, Lloyd Shapley got a Nobel Prize in 2012. And actually, this was the official citation of the Nobel Prize Committee for the theory of stable allocation and the practice of market design. The point is that this algorithm is very, very important, not just for marriage problem, but for in economics in general. And so they proved the existence. This is called what I described called the deferred acceptance algorithm by some researchers. Actually, Shapley was a very prominent game theorist, and he was actually the prize was awarded to him from work on game theory and particular Shapley value, which is very well known. Okay, so let's now look at some example and see how can we progress forward. So we quantify these preferences by man because we live in a capitalistic world. So we have these two tables for men and women. So this is the matrix for men. So the first man will get 4 gold coins if you marry woman 1, 8 gold coins if you marry woman 2, and so on. And also the women 1 will get 4, 0, and 7 according to these two matrices. And let's see what happened if we apply this Shapley algorithm. So the first round, the first man proposed to the second woman because she is the best for him. Also, the second man proposed to her because she gives 3 is bigger than 2. And the third man proposed to the woman 3 because 1 is better than nothing, right? At the first of the first round, the second woman rejects the first man because she will get 10 from the second and only 4 from the first. So in the second round, the first man who was rejected now proposed to the first woman, which is the next on his list, and she accepts, and this will end with the matching, identity matching, 1 to 1, 2 to 2, and 3 to 3. Okay, this was example, very simple example of stable matching algorithm. But now, suppose that they decide to share. So what does it mean? Each married couple don't keep to themselves what they get from the marriage. They open a bank account and they share between themselves the reward. So let's say how they share. Let's say they just split it half and half. So in this case, we take each one of them will get 1/2 of the mutual reward. So in this case, man 1 to woman 1 will get 8 because they have 4 plus 4, and so on for the others. And so now in this case, the preference list is the same for both, right? They are compatible with their preference list, the man and the woman. So let's apply the algorithm again. What is happening now? Again, man 1 proposed to woman 2, man 2 proposed to woman 2, and man 3 proposed to woman 1, right? By woman 2 rejects man 1. In the second round, the first man proposed to the first woman, and the first woman rejects the third man. And in the third round, the third man, which was rejected so far, proposed to the third woman, and we again get the same matching. This is an accident; doesn't have to be like this, but in this case, they got the same stable matching for this case of mutual sharing, which is sharing, which they share the two rewards equally. But is it really stable? Well, we can try to interchange pairs. So suppose the first pair, men 1 and woman 1, and men 2 and woman 2 exchange their partners. So men 1 marry women 2, and men 2 marry women 1. So in this case, they will get certainly they will get less because they will get 12, and in this matching they will get 21, right? And also, and you can see that for any change of couples, they will lose. If 1, 1, and 3, 3 will exchange 1 to 3 and 3 to 1, they will go down from 9 to 7, and so on for the third couple. But if we make a chain deal, so men 1 will marry woman 2, men 2 will marry women 3, and men 3 will marry women 1, they will get something more, right? So the sum of the reward, which was will be 30, again against 22, which was in the. So this batching 1 to 2, 2 to 3, 3 to 1 is more efficient because it maximizes the total benefit, the total reward that they can get over all possible matchings. So how can we make it stable? Well, there is one way to make it stable, that if they share between the share between themselves not equally, but in a different way. So suppose you remember men 1 with women 3, they had together 9. So they don't split it half by half. They will the men will get 2 and the women will get 7. Men 2 will take 4 and women 3, 7. So together they will have 11, and men 3 with women 1 will get 7. So actually, you see that in this way they can get the reward, because men 1 with women 2 get 12. That's what they have in this matching. But if men 1 will marry women 1, they will together get only 8, and which is less than 9 that they could get from the matching 1, 2, 1, 2. And so under this unequal sharing, they will make this marriage stable, right? No one of them will have an interest to marry another woman but his wife, because one of them, either he or his wife or his new wife, will have to go down in the reward. Okay, is it clear? Okay, so how to find this happy matching? So what we do is just look for all possible cuts of men and women. So Mi plus women J, the sum of them will be at least the theta ij, at least the mutual award. And on this set, we minimize the sum of the rewards. Turns out that, I didn't write it down, but let me write it here. For any such assignment Mi plus moment. If we look for all set Mi Wj which satisfy this inequality, the sum of Mi plus Wj plus Wi will be bigger or equal to the sum of theta I sigma I. Now this is the sum 1 to n. This is for any permutation sigma. Well, this is very easy to see because of this condition, right? When we sum Mi plus Wj from 1 to n, well, we can sum them in any order we want. We will get the same sign. So because Mi plus Wj is bigger than theta ij, certainly Mi plus W sigma I will be bigger or equal than theta I sigma I. So we have this inequality. And so the question is, can we find such a sharing MIWJ that we have equality? And once we have equality, this equality will also give us the stable matching by the permutation which maximize this reward. Okay. So this is a special, by the way, special case of a theory of coalition cooperative games in game theory, economy. So this is the discrete version of optimal transport. And now let's move to semi-discrete, what I call semi-discrete, which is actually partition. So now suppose we have a space X, which may be infinite, some topological space, and well, it's always easier to assume this is a compact. We assume most of the time compactness, and then we extend it when we can. And the reward of X, you can think about point X in a space as a consumer. The reward that you get is the theta I of X. And theta I a continuous function. So there are a finite number of them. And we can consider open partition. So there are, we split the space X into n open disjoint set, A1 to AN, and call A0 the complement of the union, AI. So the AI are, remember, the open and disjoint. And so we can define the stability of such a partition by cyclic monotonicity. What does it mean? It means that if we consider a chain, say X and 1 at X and K, and the last one, X and K plus 1, will be the first one. We identify the last one with the first one, and each Xi is taken from the set A, from the set AI. Then we sum chain over theta I L at XIL minus the one shifted by 1, theta IL plus 1 at XIL. We always get something non-negative for any chain. And theta 0 is we defined by 0. So think about theta as a reward. So theta I are all non-negative. Doesn't have to be, but it is more reasonable to think about this way. So now we assign a measure. There is a capacity. So mu is a regular measure on X. What does it mean, regular measure? I'll just remind you, any set A in the sigma algebra, there exists an open set containing it and a compact set containing A, such for any given epsilon, such that the measure of the complement of K mu is smaller than epsilon. That's a regular measure. That's we assume on mu. And then we look for the set of open partitions subject to M. M is a vector, M1 to Mn, non-negative numbers. So this is a set of open partition. Each AI has a measure on Mi by mu. More generally, we can think about some set K, compact set K in Rn plus, and the open subpartition with respect to K will be all open subpartition, which with M distribution in K. So we find now the polar function of K. This is, let me write it here, just because we may need it later. So P is a vector in Rn. We call it the price vector. In this example, we take K to be the simplex, all the simplex bounded by M, so all the masses below component-wise bounded by M, then evidently the polar function will be just the sum of Mi times the positive part of Pi. So this is the positive part, 0 if Pi is smaller or equal to 0. We can distinguish three cases where the sum of the masses Mi are more than the mass of the total population. We call it oversaturated. If this is equally saturated, and if it's less, then it's undersaturated. Just terminology. And what we now want to do is to find some stable partition with respect to this theta I. So we consider this function on partitions, on open partition, which sum the excuse me, here I have to put the integral AI, not x. Yeah? Sum of 1 to n of the integral over AI of theta I, and the sigma m will be the supremum of all this reward over all open superpartition subject to M, and more generally, if we have a set K of masses M, we make the supremum over this. So this is just the definition, this analog to definition that we had before of the stable matching when we, in the sharing case, where we maximize the reward of all possible matchings. In this case, the first proposition that if A is in the open subpartition is a maximizer of this function for a given M, then it is a stable open partition. And what we have to do is just to look for a cycle, to assume there exists a cycle for which the sum is negative, and use the fact that theta I are continuous and the mu is a regular measure. So we can find small balls around each point xi in AI, such that the ball is still in AI, and the mu measure of this ball is epsilon, force. Epsilon's fixed or small. And then because of the continuity of the function, we can guarantee that this sum over the integral of the small balls is also negative, right? And now we define a new partition. U at the point IL will be the union of the set AIL, the part AIL with the ball RIL minus 1, and we cut from it the closure of the ball at the point IL. And in this new partition, satisfy the condition of M open partition, because the measure of mu IL is the same of the measure mu of AIL, and because of this inequality, we see that the partition the sum of the reward for the partition is bigger than theta of A, which violates the assumption that A is a maximizer. Okay. Okay, everything clear? You can stop me anytime if you like. Okay, now there is a second way to look at it, second paradigm. Free market. What is a free market? We think about each I as a seller, which sells some good, some commodity called I. And so each client, each agent X, theta X is the surplus, is the surplus for agent X or consumer X buying the item I, and the seller charge a price PI for the commodity I. So so each one of the consumer will look for the item which maximizes profit, right? So he looks for all the possible commodities, reduce from them the prices, and choose the one which maximize. And of course, if it is going to be negative, then he's not interested at all. Well, he's out of the game. So we take the positive part of this, call this zeta plus. So this is a function of P and X, defined in this way, and we can integrate it over the whole space. Call this P plus. P plus is a function on Rn. And this defined in natural partition. It's not necessarily open partition. Generally, it's not open, but it is partition. A0 plus will be the set of all points where the commodity minus the price is negative. So this one, which will not be partial by any of the buyers. And the A plus will be the set of all points where the profit is maximum among all other items. Okay, minus this set, minus A0 plus. So we call P M equilibrium vector if there exists an open partition subject to M such that each component of A will be contained in the A plus, So AI will be contained in A plus I, P. This is true for any I, including I equals 0. Remember, A0 is the complement of the sum of AI, will be also included in AI 0 plus according to this definition. So again, we can prove that if P is an equilibrium vector with respect to M according to this definition, then the corresponding partition, which is defined here, is stable according to our definition. Again, the proposition is not, the proof is quite simple. To prove stability, we have to look at chains. So we take a chain, Xij in Aij plus. We set P0 to be 0. Then we have this chain of inequalities. Of course, theta Ij at Xij plus 1 means Pij is smaller than its positive part. And this is smaller or equal to the positive part of the same thing, but with the index index Ij plus 1 instead of Ij. So we change the index from here and here to ij plus 1 and leave the point xij plus 1, because, again, by definition, this is the one that maximizes the profit minus the price of the other, and this is smaller or equal than if you remove the positive part. And then if we sum over all the cycle, we get that this is equal to the sum of the this sum, which is bigger or equal to 0 because we have this inequality, right? Okay, this is, we just add and subtracted the prices Pij from the sum and get a non-negative because of this inequality. Okay. So again, I remind you, we define chi plus to be the integral of this function zeta plus. Then, again, very cheap, we get this proposition that for any partition, any open partition subject to M, in any price vector, we have this inequality. So the reward of partition A, sum of the reward of partition A is smaller or equal than this function plus P dot M. Well, why is this? Because definition of zeta plus, theta I at point X is smaller or equal than zeta plus Pi. So if we integrate, if we look at the theta of A, by definition, this was the integral of theta I over AI, smaller or equal than this integral, and this is just the integral of zeta plus Pi mu I, and this is smaller or equal because this integral is smaller or equal to P plus because the union of AI is a subset of X, and all the components of zeta plus are non-negative by definition, and the Mi is the mass of AI, mu mass of AI. So we have this inequality. Okay. So the next proposition is close the loop. We say that if P is a vector in Rn and A is an M partition, the inequality is satisfied if and only if P is an M equilibrium with respect to A. And well, the proof is here. Also very straightforward because first we have this inequality that we saw before, actually, and then if there is equality here and here, then we prove that since mu mi is equal mi, then this sum of the integral of chi plus is just the function chi plus p, and since by definition theta is smaller than or equal to chi plus I, we get that chi plus is equal to theta I minus pi on AI. So by definition, AI is a subset of A plus. So this was one of the condition, according to the definition that we made before on a partition which is subject to the price P. And the other direction is also quite straightforward. Anyway, we can extend it to the case where the masses are taken from a set K, and you remember the definition of the polar function. We took the supremum over all P dot S or all masses S in K, or maybe you write it M dot S. Just avoid confusion. we get this inequality if we take the supremum over all possible masses. We get this inequality. Again, if it's also possible to see quite easily that if there's a single point M, and this is the case with what's saturated, so the sum of Mi is the sum of the masses is equal to the mass of the whole mu masses of X, then we can replace Chi plus by Chi and then remove the positive part of in the definition of zeta. Okay, this proposition is also, well, we can skip it, I think, it's not very interesting. There is another way we can take it, in that direction, of a competitive matching, because you see, if X is an agent, if agent X is a consumer and agent Y is a seller, then and Chi plus is the way that we defined it before. Formally, obviously, this is a convex function by this definition because it's a maximum of a linear function, linear convex function. Positive part is a convex function. And its subgradient, I will say something about it later in more details, is just the measure minus the measure of the set AI. Formally, if you differentiate by PI, we get 0 except all the points where the maximum is attained. And then it's an integral of -1 on the set AI of P by this definition. So what is the profit of the seller I? The profit of the seller I is just the amount of that he sells is the mu of the set AIP. That's the set of its clients, the number of its clients, times the price he charged. So this is just minus PI times the subgradient of set. And then we can look for Nash equilibrium. Nash equilibrium means that each seller, there is a price P1 to Pn, such that each seller will not gain anything if we change its price, assuming that all the other prices are fixed. Okay? This is the definition of Nash equilibrium. I will not pursue this direction. But this can be a very interesting question to look for about the existence of Nash equilibrium in this function. Fis defined here are quasi-concave. This is a condition for existence of Nash equilibrium, but we will not follow this direction here. Let's see how much time do I have here? So now it's 5 minutes. Okay. So let's summarize what we know. So this is a theorem. If A is an open partition subject to N, then these all are equivalent. A is clever partition, if and only if there exists a price vector, P and an equilibrium M corresponding to A, if and only if A is a maximizer of respect to theta in the open subpartition set subject to M, or if and only if there exists a minimizer P of this function, the function of P, and the set A is contained, each component of A is contained in the component of A plus. So actually, we didn't prove everything. We proved anything except from that one that one implies two. That's the thing we didn't prove. And let me spend a few minutes to prove this, because this will be very, very important later when we talk about the real problem, the full problem. So what we have to prove is that if it is a stable partition, means that if we have what we call the cyclic cyclic stability, then there exists such a price P, equilibrium price P. So how we build the equilibrium price P out of the stable partition? So so if we have a stable partition, then we recall we have this equality for any chain, right? The chain started with I1 and end with k, where ik plus 1 is I1 again. And now we replace, so we look at this and we replace theta I1 xik by theta I xik. And look for all possible chain and define Pi to be the supremum of all possible chain, right? All possible chain where in this definition we replace the first theta, the first theta in the chain by I, evaluated at the same point. First, it follows that P0 equals 0. Why? Because theta 0 by definition is 0. That's why that's how we find it. And because of this inequality, if we replace theta I1 by 0 and theta are all non-negative, we assume, then this is will be always non-positive. And if it's non-positive, the circle will be 0. So theta P0 is 0. And now let's assume that take some alpha smaller than Pi and choose a chain which realizes this inequality, because according to the definition, we can find for any alpha smaller than Pi, we can find such a chain. And we add theta jy minus theta iy to both sides. So again, look at this. And then we just add the same thing to both sides. Theta jy minus theta iy, here and here. And so the right side is smaller than pjy because this part is just a cyclic permutation of k plus 1 cycle, which is corresponding to I1 to ik plus 1, and ik plus 1 will be I, and ik xik plus 1 is y. Yes, and so this is just a k plus 1 cycle, and by definition, pj was corresponding to j, right? So by definition, this is smaller or equal to j. So it follows that theta iy minus pi is bigger or equal to theta jy minus pgy. This is for any y in a I. If we set j equals 0, we get this is non-negative because this will be 0. And hence we have this inequality. And this implies that A is a subset of A plus, because if we choose this P that was defined, was constructed by this way. So the cyclic symmetry imply the existence of this price vector. Okay. All clear? What time I have finished the talk? How much time do I have?
About
15 hours. Okay. Okay, I hope I'm not going too fast. But, so let's now go to the full problem, step by step. So the next step will be consider topological spaces, and I will give you some reminder of, because so far what we had is X was a compact space, a compact measure space, and the target was discrete, was the point 1 to n was a discrete point. Now I want two spaces to be possibly infinite. So I look for weak-star convergence. Remind me of the weak-star convergence in Banach space, Banach-Haloga theorem, which says that the unit ball in a separable space, Banach space under the weak topology is compact. We assume that X is a separated locally compact metric space, and in particular, consider the space Cx as a continuous function, C0x, which is a space of all functions which are decaying to infinity, which means that for any epsilon, there exists a compact set such that F is smaller than epsilon outside compact set. This is C0, and Cb is just the bounded continuous function. Of course, F is compact, then all these three spaces are the same. Rising representation, any Borel measure, it can be identified with the dual C0. A weak star convergence in M is duality with C0. Narrow convergence is in duality with C bounded. Okay. The weak star limit, well, P of X is a set of probability measures. That's, we're not talking about probability, but that's just convenient to call it this way because this is normalized measure. It's non-negative and the integral is 1. This is P. So if we take a sequence of probability measure, the weak limit of sequence of probability measure is not necessarily probability measure because 1 is not in C0. Yeah, but on a compact space, this is always true, and this will be very important when we talk about Kantorovich duality and the Kantorovich relaxation of the Monge problem. So there is a Poincaré theorem that says that a set A in P is a probability set is tight, which means that the integral with respect to some function which goes to infinity is bounded. Then the set is compact in the normal topology in duality with bounded function, and the notion of a Polish space. This is a separable and metrizable with a complete metric. Okay, now let us look again at the Monge problem. So first, assume that X and Y are compact spaces and have a Borel signal algebra. And what is and T is the mapping from X to Y. What is T? How T push forward the probability measure mu to nu means that for any set in a sigma algebra of Y, the measure nu of A is equal to the measure mu of all the sources of T-1A. Equivalently, for any continuous function, this integral is the same. So this is the equivalent condition to this. T has mu equal nu. Monge problem, like I said at the beginning, is just find the infimum of all mapping T of mu equal nu, so between ds mu equal mu, of this integral with respect to the cost function C. A certain cost function C, which point, let's say a continuous function of xy. What is the problem here? The problem here is that the set of all mapping T which satisfy this constraint is not a compact one, and certainly not a linear one, right? Like a combination of such mapping, a linear combination of such mapping is not in the class, right? So, so if we want, for example, we can talk about the infimum, but certainly we cannot say anything about minimum in this definition. So Kantorovich, like I mentioned before, in 1942, he considered the following relaxation. Let's look for all 2-point measures, gamma, in the set probability set on x times y, on the Cartesian product of x and y, which has marginals mu and nu. So this is pi x is the projection of xy on the first component, and pi y is the projection on the second component. And by this definition, this is just the push forward of the projection of gamma is the measure mu on the space x, and the push forward of the measure gamma by pi y is the measure nu. So this is you can immediately see that this is a convex set of measures in the probability measures on x times y. And then we say, let's look of the minimum, not of the mapping, but of this probability measure in the set pi mu nu. This is a great relaxation, right? Not why is it a relaxation? If we have a mapping T which push mu to nu, then according to the definition of a push forward, it means that the identity, if you consider the map which acts as the identity on the first component and then T on the second component, and push T to the second component of acting on mu, this will be a measure in this set pi mu nu. So, because if we call S this map T, it's mapping from x to x, y. So S of x is x dx. Then we take the integral of as a function of p of xy on the push forward of S mu. The definition is just phi at x dx the mu. So this is just the object that we looked for the Monge problem. So any such mapping T induce a measure in pi. So to take the minimum on a larger set, we get something smaller or not bigger. So the Kantorovich price pk of mu nu is always smaller or equal to the Monge cost of ni and mu. This is just from the definition. And when you can think, well, usually this is a strong inequality because we make a huge relaxation. But in fact, there is a somewhat surprising theorem that says that if mu has no atoms, NC is a continuous function of two variables, then we have equality. Equality means that just the infimum of the infimum of the Monge problem is equal to the infimum of the Kantorovich problem, and And again, you can guess now that the infimum of the Cantor-Horowitz problem is always attained because of compactness. We'll see in details soon, but here we always have a minimum. That's the real advantage. Here we don't necessarily always have a minimum, but there is a quality on the of the infima of both. And why is the condition of atomless? Well, of course, if mu has an atom, then T of mu will also have an atom in the image of weight of at least as the atom of mu, because T cannot T push one point to one point. It cannot break an atom. So being having the atom for mu is a very strong restriction on the value of the measure that T can push mu. So this is a nice theorem, and I will think I give you a proof. The proof is not very trivial, but time to finish or 5 minutes? Okay. So I will start, and maybe I will finish tomorrow. So here is the proof with certain steps. First, by the way, this proof and some of the stuff I will present later is taken from a book of Sant'Ambrogio, which is an excellent book. I recommend it for everybody. This is a very friendly book and rigorous and very nice, very easy to read. It's also not its original proof, but I think this was given, the first one who gave this proof. The first, we show that for any two measures, probability measure on the real line on R, if mu has no atom, then there exists a Borel map which push mu to nu. This is true for any two pair of probability measures on the real line. What is the point of the real line? In the real line, we can define accumulation function. This is just the measure of the interval between -infinity to x, the measure mu of the ray from x to -infinity. So this is monotone, and it's continuous. Why it's continuous? Because the mu have no atom. If you had an atom, then we have a jump at the atom, right? If x has an atom, then this f will jump. But if mu has no atom, then f mu is continuous. And what actually f, if you think about it a little bit, it pushes the measure mu to the Lebesgue measure on the interval I. I is the interval from 0, 1. Forgot to specify. Okay. Well, you can use this fact that the derivative of f is actually the derivative of u with respect to x, the Radon-Nikodym derivative with respect to Lebesgue measure. It has a pseudo-inverse, because it's not always strictly monotone, can be flat at some point if the measure mu is 0 on some interval. So, but we can define the pseudo-inverse in this way. We take the infimum of all t, such that f for measure nu, such f nu t is bigger or equal to x. This is the real inverse if f is strictly monotone. And then what x mu do is push the Lebesgue measure into nu. Nu here. X nu push the Lebesgue measure into nu. So if we compose these two, we get that compose x nu over f mu, this push mu to nu. So we proved this part that we can always find a Borel map which push mu to nu. The second statement is we can always find an injective Borel map from RD into R, not onto into R, such that its inverse is also Borel. And it's enough to do it for dimension, to show it for dimension 2, because by induction argument, we can define the dimension, we can define the mapping dimension D to be the mapping in dimension 2 acting on x1 and the function d minus 1 on the rest of the components. So this composition is also Borel, right? If sigma 2 is Borel. And sigma d minus 1 is Borel. For any d, then we define sigma d. So it's enough to do it for d equal 2. And we do it in this way. Look at the unit interval again. The unit interval is equivalent to the whole real line. Just take arctangents or something, map it, the unit interval to the whole line. And in the decimal expansion of each point, of 2 points, we consider the alternating decimal expansion A1, B1, A2, B2, and so on, right? For number x1 equals 0 dot A1, so on, and x2 0 dot B1, B2, and so on. We can remove all numbers which are ending with 9999, infinite string of 9, and representation by 0. So this gives us just a measure of 0. The rational numbers, the big measure 0, they don't count. So, and we define this mapping, and we can see that this is a Borel. This is a pre-image of any rectangle determined by the first k digit of its component. The interval in R, which is determined by the first 2k digits, right? So, so both this mapping and its inverse is Borel. So this is proof the second. So we now know that we can map RD into R by a Borel map back and forth. The next statement is that we can approximate any probability measure by partitioning the set omega into cells, into small cell W i's column of small diameter. And so we can replace mu by some measure mu n, which is this is the same thing, wi, should be wi, not omega I. So mu n is just a measure which gives for any part wi the same measure as mu. I don't specify what mu n do inside the set wi. I just say that for any wi in the set, in the partitions, in the part wi, it gives the same measure as mu. And so look for a sequence of measure mu n like this, where the diameter of the partition goes to 0. Then mu n converge weak star to mu. And converge to infinity with the diameter wi uniformly goes to 0. So this is also very quite straightforward, quite obvious, because by definition of weak convergence, right? Because this is the weak convergence. The weak star convergence is by duality with continuous function. And when the diameter goes to 0, then the variation of each continuous function wi shrink to 0. So the difference between the integral mu n to the integral mu over the whole space may become smaller as n goes to infinity by this. Okay. Now the last step. We show that a set of Borel maps are dense in pi mu nu. That's what actually we have to show, right? Because this will give us the quality of the infimum of both of Borel and Kantorovich, right? So let's take gamma in this pi, in the set pi mu nu. So make a partition of set omega into small cells and look for the composition mu I mu j. We assume here that x and y are the same space, not limitation to the relativity assume this. So x and y, or they're both, I call them both omega. Right? And so we make a partition of omega and look for the composite, the tensor product of the partition of omega plus omega. So let's restrict gamma to the set wi times omega, call it gamma I, and then mu I and nu I will be the marginals of gamma I. So mu I will be just the marginals of mu, right? But nu I is the marginal of this gamma I, which is, let me sketch this to make it. So this is the partition. And this will be, this where gamma I lives. This is the omega x, and this is omega y. And this is when gamma I lives. So because mu I is just a restriction of mu, it has no atom, then by the first claim there exists a Borel map which push mu I to nu I. Yeah, this is because, well, the first two steps, there exists, if they're one-dimensional, there exists one. If they're more than one-dimensional, we can map it to one-dimensional space by this mapping, Borel mapping that we saw before. So let's define Tn to be the union of Ti. That's the sum of all Ti. And then Tn push mu to nu, because the sum of mu I is mu, and the sum of nu I is nu, and the sum of mu I is mu, right? By this definition. So we defined the measure gamma n to be the push forward of mu by identity and Tn. And then we see that the measure gamma En as we defined it is actually equal to gamma on the same on Wi times Wj, because by definition, what is gamma nt is just the measure of mu at x in Wi, but Tn is Wj. That's the way we define gamma Tn by this push forward. So this is mu I. So because mu is equal to mu I on Wi, we can replace mu by mu I, right? Because this is the same, right? Mu restricted to mu I, to Wi is just mu I, so we can put it like this. And then we can remove the condition x in Wi because mu I is anyway supported only on Wi. So we can remove this I here. so we can remove this condition. So this mu I of x in omega and Tn x in Wj. This is by definition just mu I of Tn in Wj because the first condition is redundant. And this is by definition mu I of Wj. This is just the marginal of gamma defined on Wi, Wj. So not the marginal. This is actually we define mu I to be the push for in this way. The marginal of gamma defined on this set Wi times omega. So we have this equality. Two measures, gamma Tn and gamma, agree on this partition, true for any partition. And by the theorem of the continuity theorem, it means that they are, that gamma n of T converge tau weakly to gamma. That's it, right? Okay, just finish the proof. Just finish the time also. No? And to